The last video we started talking about how to get started doing refrigerant checks, looking at your saturation pressures and air temperatures and things of that nature. Okay, so in this video I'm going to spend a few minutes talking about superheat and how I go about thinking about that. If you haven't refreshed yourself or familiarized yourself with what the definition of superheat is or subcooling, then I highly recommend you do that. It is it's not a very hard topic to get a hold of, but it does take some thought. Okay, a lot of people will talk about the boiling point, but you have to remember that it's not just the boiling point, it's a saturation point. With the pressure moves the saturation point, okay, because we're boiling in the evaporator and we're condensing in the condenser. All right, so it's not just boiling. But I'm going to draw some things on the board behind me, and like I said, we're going to look at what superheat, kind of how I think about superheat. I know what it is. Superheat is the heat above a saturation point. So if my saturation point in the evaporator is 42 degrees, if the vapor temperature in the vapor line going back to the compressor, if I measure that line and I get 43 degrees, then I have 1 degree of superheat. So it's once you complete the phase change for both superheat and subcooling, right? So we're changed all the liquid to a vapor, or all the vapor to a liquid, what have you. We're going to do something special with that. Okay, so that's where the superheat and the subcooling realm is. But superheat is heat above saturation, and subcooling is cooling or rejecting heat below the saturation point and making that liquid cooler. All right, so please do your research on it. But what I'm going to show you is how I think about it and how I start to use it to diagnose systems and kind of get it in my head. Just for reference, right? You probably already know this, but keep it in your mind still. The calculation for superheat is going to be our vapor line at the end of the low side, right before it goes in the compressor if you want to. But the vapor line temperature minus your evaporator saturation temperature that you get from your gauge. All right, based on the pressure, you'll have a certain saturation point. Vapor line minus your evaporator saturation temperature gives you superheat. That's the calculation, that's the formula. Subcooling is our condenser saturation temperature minus the liquid line temperature. All right, liquid line is, it connects to the metering device. You can, if you want to get the full reading, you can get it right before it goes into the metering device at your evaporator. We tend to get these numbers right for the vapor line and the liquid line. If it's on a split system, we tend to get them at the service valves, and that's industry acceptable, the whole nine. But you got to check them. This is the stuff that tells us about the refrigerant. Okay, it tells us the state, tells us how much. Right, it's all part of it. So superheat, subcooling, get it in your head. All right, so behind me I've drawn out just a simple sketch of the low side of a system. This is just a standard R410, residential refrigerant circuit, nothing fancy. But we're going to talk about a couple things and get into superheat just a little bit. All right, and like I said, how I think about it. All right. So of course we got our compressor at the top, which is the end of the low side. We've got our metering device at the bottom, which is the beginning. So we're basically going to have our liquid line coming in, right? I would draw it in red, but the red marker is way over there. So our flow is going into the metering device. And if you've familiarized yourself a little bit or done any reading, then you'll know that this high pressure side, the liquid line, ends at the metering device. And where it starts the beginning of the low side, we have this little phenomenon, right? This little situation that occurs, and it's called flashing, or a lot of people will refer to it as a flash gas. When you have a very warm liquid refrigerant going in and it goes through that pressure drop, then it comes out at a lower pressure and a different saturation point on the other side. So you think about a small piston, an orifice, a half an inch wide, and it's got a small hole in it that's not even the size of 1/8 of an inch. There's a lot that kind of goes there. Flash gas for me kind of sits in, and for a lot of people that I see, starting out, it kind of messes with you But the easiest way that I could describe it, right, if you remember the laws of thermodynamics, we cannot create or destroy any of that heat energy. It has to be accounted for. Something, somewhere, somehow accounts for that. So if we had a 40-degree saturation point because we had 119 psi on the low side of our system, and let's say that I had a 100-degree subcooled liquid coming into the liquid line, where does that 100-degree liquid just turn into a 40-degree, liquid on the low side, right? Something has to account for that loss in temperature. Flashing or flash gas is a way that we kind of reconcile that and get it in our heads. This flashing, some of that liquid refrigerant coming in, as soon as it got out of that metering device, we had to give up a certain amount of heat to account for the difference between the two sides, right? You can't destroy it, but you can move it around, okay? You can account for it other ways. So flash gas starts off our low side, and some of that liquid refrigerant instantly changes into a vapor due to the pressure drop and the temperature of that liquid coming in. When it comes out, that's just the way it is, okay? And like I said, this is my 2 cents. If you've got another way to explain it, please let me know, okay? But the simple way is, that's how we account for it, right? The change from that 90 or 100-degree liquid coming in, and now it's a 40-degree mostly liquid mix coming out. We lost 40, 50, whatever degrees there. The higher the difference between that liquid on the high side and coming out into the low side, the more flashing you'll have, and that takes away from our net performance, right? So we've already turned our 100% liquid coming from the high side into a saturated mix, okay? It is a liquid vapor mix right there coming out of the metering device, all right? So we're not 100% liquid anymore. Some has changed, okay? But that still doesn't take away from the fact that now we're at a 40-degree saturation point, okay? So starting right here and going all the way into the coil, we have a liquid line, a vapor line, a discharge line. I don't know anybody that calls this line that connects the metering device to the evaporator. There's not really a specific thing. It's more of a distributor area. But that doesn't make any sense either, because we do it on both coils going in and coming back out. So enough about that. But if our low side is a 119 psi, 40-degree R410, we got a saturation point there. What does that mean? That is what a lot of people will say the coil is working at, the temperature at which everything is happening. It is in fact a boiling thing, because liquid refrigerant is absorbing heat. We have 400 CFM of air hopefully going across our evaporator coil, and it's bringing in the heat from the house or the space or whatever office, and it's keeping that saturation point and that pressure there. Okay, the heat being brought in by the fan keeps it there. If we didn't have the heat, it would drop. Okay, so our coil is active with this, like I say, where the latent process takes place, where we're changing state, is where we do the bulk of the work. All right, so by having a liquid vapor mix and that refrigerant being in that state and changing states, right, it starts out mostly liquid, but by the time we get through the evaporator, it should be vapor. All right, so if we just said that it was mostly liquid right here, if it's 80% liquid going in at this point, as we get into the coil and that fin coil, right, more surface area for the airflow to go through and across and more heat to absorb, right, it's easier. Then eventually we're going to change all that liquid into a vapor. So we start out with mostly liquid, but we'll end with hopefully all vapor. And usually, we'll just say that happens right here. All right. And the refrigerant has done its job, right? It's absorbed the BTUs that's needed, for the system, the whole 9, right? Whatever it's rated for, 1 ton, 2 tons, 10 tons, what have you. At this point, when we have finished the change of state, right? The pressure temperature chart does not apply anymore. There's no more liquid there. We're not a mixture of the states of refrigerant. Okay, A lot of guys say it's not a saturated mix anymore. It is 100% vapor, okay? At that point right there, that's where your superheat starts, at the 100% mark, because we're only going to finish going through the coil and we're only going to add more heat to it, okay? And that's the definition of superheat, heat above saturation. So once we get higher than this, okay, you may check your pipe temperature and it's 41 degrees, 42 degrees, 50, 51, 52, whatever it's going to be. You have to take a physical line temperature. But superheat will start wherever that 100% mark is, and of course depending on charge and the load and everything like that. And that vapor will continue on and eventually wind up being pumped by your compressor, okay? So we got the definition. You should be doing some homework on it. But understand, for me, superheat, when I hear superheat, really what I hear is vapor. Superheat lets us know that we have changed all that liquid refrigerant into a vapor, and especially for our compressor, that means that we're not going to pump any liquid through it or attempt to, okay? We're not going to slug it. We're not going to have any foaming or anything like that, okay? So what number's the best for superheat? Well, the book, a lot of books that you'll read, they'll tell you 8 to 12 degrees, maybe 10 to 15 degrees of superheat. That's what's recommended, okay? The fact that you have 1 degree of superheat should let you know that you have vapor there, but there are, normal numbers that you should shoot for. Like I said, a lot of books, they'll tell you somewhere around the 8 to 12 mark, and that's fine. But what does that mean? I tell a lot of my guys, you should be estimating what you should get, and then you need to verify and, of course, hook up your gauges, take temperatures, all your readings, and verify what the system is. But how do you go about thinking about it, all right? So this is me, all right? I like to start at the end of the circuit where I know the superheat's gonna be ending, right? So for the low side of the system, for the evaporator superheat, not mentioning anything about compressor superheat, but for the evaporator side, we know it ends at the compressor. So if I were to say have 1 degree of superheat, what does that mean, all right? How do I think about that? Well, I like to put a little mark, like I said, since we have just a 2D kind of version of this, I like to put a mark right there. So if I said I had 1 degree of superheat, then that would mean that I did get 100% vapor. I'm not going to slug the compressor with liquid, but that 1 degree, which is not as much as 8 to 12 degrees, right? So we'll just say 8 to 12 is normally right there. But 1 degree of superheat means I got pretty close to that compressor with that liquid. Maybe I didn't have enough airflow, maybe I didn't have enough of a heat load on there, maybe I have too much refrigerant, but I got real close to going in my compressor with liquid. If I had 5 degrees, right? Maybe 5 degrees is, right here. And it's all interpretation, but it's further back if I actually had 5 degrees of superheat. All right. If I had 10 degrees or 12 degrees, we could say that's here. All right. The more superheat that you have, what if I had 20, right? If I had 20 degrees of superheat, we could mark that spot right there. The more you have, the further back from the compressor it actually happened, which means the sooner that my liquid went away. If you have an undercharge of refrigerant, your refrigerant, you don't have enough refrigerant going very far in your coil to do any good, okay? What you do have is going to quickly be hit with heat, and it's going to change into a 100% vapor, and then it's pretty much done moving heat. It has to be cycled back around and through. So when you have a high superheat, which is very, one of the things we look at when we talk about a low refrigerant charge, why do you have a high superheat? Because for the amount of heat that you have, it quickly, right, early in the coil, early in the circuit, it basically handled the refrigerant and turned it all to vapor. So the larger the number, the further back in the coil it happened, okay? And, this is, we had guys that get like 40-degree readings and stuff like that for superheat. If you do the formula, you can get hundreds of degrees of superheat. But that's the math formula. That's not kind of realistic, So just understand that with superheat, it's heat above saturation, which means we have turned all the liquid refrigerant into vapor. But when like I said, me personally, when I think about it, the larger the number, the further away from the compressor it happened. And if we go too far, you'll find that your coil is not even active, okay? So I hope that helps. I know it's not a complete, you know, kind of deal, but just to kind of get your mind wrapped around it a little bit. All right, so now we're going to flip-flop to the high side of the system, the condenser, and we're going to talk about subcooling a little bit. I write in red just for the high side, so subcooling, don't get the colors mixed up. You think cool is blue or whatever, but anyway, the high side of the system. We just talked about superheat into, or at the end of the evaporator side, and it goes into the compressor, right, into the vapor line. We have a discharge line here as well, right? So once we get that superheated vapor off of the low side, it may be 50 degrees or 60 degrees. A lot of people think that's very cold, very cool, and it is. But by definition, superheat is heat above a saturation point. Doesn't matter the temperature. It's the definition of it. So we've got maybe a 50-degree vapor, refrigerant vapor going in our compressor, and that vapor is, the way that I like to think about it, just to get people started on it, what keeps that sealed compressor cool? The refrigerant vapor that's passing over it, right? It's absorbing the heat from that motor, right? So we're still going to continue the superheat process even in the motor, and once we get out of the compressor, right? Once that compression happens, that heat of compression, all that heat is going to be added to that refrigerant vapor that's superheated already from the low side, but it's still superheated a little bit more in the compressor, and then we discharge. The first big job of the condenser is going to be to de-superheat the refrigerant, okay? So I've got it broke down, the three main jobs of your condenser is de-superheat, condense, and then we start our subcooling process, right? So as we exit the compressor, that warm refrigerant vapor, right, it's definitely 100% vapor already. It's going to get into the coil, get into the airflow, and it's going to start to lose heat. And it's going to do it, you know, fairly quickly, but we'll go and use the first little portion of the coil to get rid of that excess superheat, right? To get rid of that, well, not excess superheat, but get rid of all that superheat. We undo the superheat over here, right? The evaporator absorbs the heat, condenser rejects it. The first little portion of the condenser coil is to get rid of the superheat, because whatever pressure our condenser's at, we'll just say it's 340. That's about 105 degree saturation point for R410A. All right. We have to get that 140 degree vapor down to 105 degrees, right? We have to remove that extra sensible heat, that superheat, so we can condense it, right? It's not a boiling point, it's a saturation point, because on the condenser we don't boil the liquid. We don't have any liquid to boil yet. We are going to cool that vapor down, right, to the point of saturation where we can actually take enough heat out to make liquid. So we de-superheat initially, we get into the condenser, and we're going to cool it down. Same thing as the evaporator. The bulk of the work is going to be done in the coils. We're changing state, and that is where we absorb and reject the most heat. All right. So it's a latent process for the bulk of the work that we want to do, and we condense. All right. So we're going to take that, like I said, 140 degree superheated vapor coming in from the compressor and the evaporator, and we're going to initially reject a lot of sensible heat. Once we get down to that 105 degree saturation point at that pressure, right, 340 or so in this example, then we're going to do our change of state at 105 degree saturation point. So all that liquid, all that 100% vapor is going to start to turn into liquid at 105 degrees, and we're going to lose vapor and make liquid. And eventually, we'll turn all of that into 100% liquid. And that's, right, since we're talking about subcooling now, and that's really the focus that I try to do it or try to put on this. Once we make 100% liquid, right, we are no longer concerned. I mean, the saturation chart, the pressure temperature chart, that number, that saturation point is a reference point now, because we're going to calculate subcooling. What is subcooling? Subcooling is cooling of this refrigerant liquid below the saturation point. Superheat is heat above the saturation point. Subcooling is cooling below the saturation point. So if we had a 340 psi high side pressure, that's 105 degree saturation point. Once we make all liquid, we still have a little bit of the condenser coil to go through, typically, right? The fan is still moving air across it. We're going to reject heat. We're going to lose heat. So we're going to make this liquid refrigerant cooler than 105. And that's subcooling. Subcooling is a reference to liquid. Superheat is vapor. Subcooling is liquid. We have to have liquid refrigerant going into our metering device so we can start that flashing process and the whole thing again. But we need to know we have liquid. And how do we do that? We're going to check our liquid line temperature, right? Just like we check the vapor line temperature for superheat and compare it to our saturation point. We're going to check our liquid line at the end of the coil. Superheat's always at the end of the evaporator. Subcooling's always at the end of the condenser, right? We're going to check that liquid line temperature and reference it to our saturation point. So just to get you an idea of how I think about subcooling, it's very much like superheat, right? I know where it ends. So the further or the closer to it, right? I might have 1 degree of subcooling. Oh, then my 100% liquid point happened very close to my metering device. 5 degrees of subcooling. Oh, well then that happened a little further back. I've got a little more liquid, so I've got, you know, more liquid in the line. It happened a little further back towards the coil. Oh, I've got 10 degrees of subcooling, right? Oh, right there. Right. Something I didn't put up there, but the books will tell you that subcooling is probably going to be 8 to 12 degrees, maybe 10 to 15 degrees. You can look at manufacturer specs and stuff like that, but what does that mean, right? So 1 degree, very close. We barely made liquid in time. 5 degrees of subcooling. Well, we made a little more liquid. Still not great. We, you know, if we go with the recommendation, we, you know, 10's a good number. But what does 10 degrees look like? Oh, it happened kind of in the coil, right at the end. What about 15 degrees of subcooling? Further back, right? 20 degrees, what have you, okay? And of course, this is not the spec, this is an idea. The more you have, or the higher the number, the more liquid you have, and the further away from that metering device that you're filling up with liquid, okay? I hope that made a little bit of sense. I don't mean to rant and rave too much. I just, you know, some of the basic stuff that people don't try to understand, I want to help out as much as I can. It's a great field, it's been good to me. Summers get a little brutal, winters get a little cold sometimes, but this is, you know, it's basic knowledge that you got to understand, that you got to want to understand. There's always something more to learn. I hope that each and every one of you will go out and try. This is just my 2 cents. I'm not perfect. I misspeak, and I put crazy numbers sometimes in the examples or whatnot, but it's just in an effort to kind of help. So I appreciate you watching. Appreciate the comments and everything. Until next time.